Record. Hello, welcome back to Organic Chemistry 2330. I apologize for not having your grades up for the exam. I plan to have the grades and all of your homework from 1 through 7 already posted. Okay, the score you see on top hat is the raw score, and it's going to be curved when it goes to Canvas. Unfortunately, I had to take my father to the hospital and I didn't have time to and stay with him all weekend, and so I didn't have time to convert the exam. So I greatly apologize for that. I will try to have it up by tomorrow, and so that by our class time on Thursday it should be there. Okay, so you know, it's been a very stressful week for me, as but taking the exam hopefully was not that stressful. Okay, so again, it should look familiar on the next exam. You should look at what you should be studying as like the homework questions and those top 3 takeaways from each chapter. I think that is going to be doing. My father is doing better. He's back home, but is undergoing a little bit of rehabilitation with, you know, physical therapy and stuff. So it's hopefully getting better. So we'll see about that. All right. Thank you very much. Okay, so let's shake out that exam. We had 7 chapters that we covered in that one, right? We learned about what the bonds were. We learned about what leaving groups were. We learned about our priorities on how to name things, right? And so up to now, we've been using chemistry that only use the infix and the prefix with an E. We only had hydrocarbons because halogenated materials don't change that prefix. Today, we're going to actually start changing the prefix by looking at alcohols, ethers, and thiols. Okay, so that's chapter 8. And so I'm going to go ahead and share my screen. And I think it's that one. Yes, there it is. Can everybody see that screen? Those pretty peacock feathers there? Okay. And I'm going to move the gallery view up over here. Okay. All right, so this is chapter 8, alcohols, ethers, and thiols. So now this is the first time we're changing that suffix, that changing the end of the name. And we're going to talk about how to name those things. And then we also have a very closely related compound, the ethers, but ethers don't change the name. They are always a substituent. So we're going to go through and name some of those, including some common names for these, as well as some of their physical properties. Okay. So alcohol has to have an OH group on there or a hydroxyl group. Okay, the oxygen is sp3 hybridized and the carbon it's bonded to is sp3 hybridized. That gives rise to their shapes. That's why we have on the hydroxide 2 lone pairs and then 1 bond to oxygen and 1 bond to hydrogen. Okay, well, because it's sp3 hybridized, it has an approximate bond angle of 109 degrees. It's actually a little bit less because the hydrogen doesn't take up as much room as like some of the other ones. And so it's a little bit less, about 108.5. And the lone pairs are actually taking up a little bit more room. Okay, so that's why there's a slight decrease in angle from the 109.6, the 109.5, the theoretical, but it's those lone pairs. We have to remember those lone pairs are there when we're looking at the shape of the molecule. Okay, so because it's our first group to change the name, we have to remove that E at the end of our line and add the all. Note, the prefix, the infix still can change, okay? And so all the attachments and the prefix and the infix can change, but we always tack the OL on at the end. And so I have a special rule on how to use the infix, and I'll get to later. So we'll do that in a couple examples, but they also have a lot of common names. Okay, so like for example, we don't call it, let's see, it would be ethanol, it's called ethyl alcohol. So when we have a common name, we just take the length of the chain, the group that it is, the alkyl group that it is, and take it as an alkyl group. So it's got to have the YL on it. So ethyl alcohol, methyl alcohol. And so our common names are going to go that way. So we have our Iupac name and our common name to play with. So in the case of our Iupac name, we're going to do our infix, our prefix right here. The F is our prefix because we have 2 carbons. The Al is our infix because we don't have any double bonds. And the OL at the end is our changing the name because of the functional group. Okay, so that way that Iupac system works completely. All those rules we've already learned apply here. Okay, so in the case of the next one here, we have 3 carbons, so that's going to give us prop. We don't have any double bonds, so it's AN, and we have an alcohol, so it's 1-propanol. Okay. However, in the common name, because it's the propyl group, we'll name it propyl alcohol. Okay. Now notice we have that 1 there. If you have the alcohol at the end, it's typically understood to be 1, but it's always proper to add the 1. Okay. So when we move over next to changing the position of that alcohol to that 2 position, that becomes the Iupac name 2-propanol. However, this now, because it's attached here, it looks like an isopropyl group. And remember that isopropyl group is those 2 methyl groups hanging off and attached in the middle, and therefore we call it isopropyl alcohol. Now, there's only 2 isomers available to us on isopropyl alcohol, and there are no isomers available to us on ethanol. However, when we get to butanol, we have 4 different isomers available to us. We have the simple one with at the end of the chain, and we call that 1-butanol. And it's a long straight chain, it's the butyl chain, so we call it butyl alcohol. Okay, if we move that over 1 carbon to give us on our 2 carbon, the Iupac name is 2-butanol. However, this is now the sec-butyl group because we have our bond on our secondary carbon here. So that's our sec-butyl group, and so it becomes sec-butyl alcohol. Now, if we move it over, rearrange, instead of moving the methyl group over, instead of moving the OH group over, move a methyl group, we now end up with this group here, which is our isobutyl group. Our isobutyl group is the one that looks kind of like isopropyl, but it has that extra carbon. And therefore, we have isobutyl alcohol. If we look at it from an Iupac name, our longest chain is 3 carbons, so it's propyl. So we have 2-methyl, 1-propanol. Okay. Now, if we rearrange that again to give us what we call our T-butyl group here, that's T-butyl alcohol or tertiary butyl alcohol. But the Iupac name is still, the propyl group is still the longest chain in it. And we have a methyl group and the hydroxy on that number 2 carbon, giving us rise to the 2-methyl, 2-propanol. And then when you have a ring, you just name it for what the ring is, in this case, cyclohexanol, or the common name, cyclohexyl alcohol. Okay, those rules are pretty straightforward, right? We're using the infix, the prefix, and the suffix to locate everything in our system. Okay, admit, there we go. All right. So let's apply that, and we're going to apply it. I want you to do it outside. We're going to do the 2 middle ones here in class, and you can go ahead and do the 2 other ones by yourself and see if you can get them correct. So the first thing we do is we do what we always do, look for the longest continuous chain. So in the case of the first one, I'm going to think it's 1, 2, it's going to be that is our longest chain possible. Note that this would be the same as that, so we can choose either one of those in our name. And because it's changing our name, we have to number with our name changing group at the lowest point. So we have our 1, 2, 3, 4. Okay, so there's no ambiguity here because the alcohol is changing the name, so we have that to be the lowest number. And that puts our substituent here on number 4, which gives us a total of 5 carbons in our longest chain. So we're going to have 2-pentanol is our main chain, but we have a substituent. Oh, there's a dash there. And so we have 4-methyl 2-pentanol. Okay, so we just apply all those same rules. Okay, now in the case of this right here, the OH again is changing the name, and in rings, whenever the name is changed, you always put that as your 1 position, and then putting your substituent at your lowest position. But we have stereochemistry. Okay, we have one of the groups with a solid wedge and one of the groups with the dashed wedge, which means they are opposite each other and they are fixed in space. And so we're going to call that trans. That's the ring naming that we use in rings, is when they're opposite on opposite sides of the ring from each other, we can use the word trans. So we're going to have trans at the front of our name. Trans here. We have 6 carbons, so that's going to be cyclohexanol. Cyclohexanol. And we don't have to put the 1 because we're naming it for that cyclohexanol. And we have our functional group, which is going to be 2-methyl cyclohexanol. So we have trans 2-methyl cyclohexanol is our complete name. Okay, so go ahead and finish those 2 other ones on your own and make sure you can name them using those proper rules. Questions on naming alcohols in the Iupac system? Okay, so just like if you had an alcohol.
I have a question.
Yes, go ahead.
So the wedge that is in the opposite space, that's just the methyl?
Correct. Yeah, if it remember, it sticks count for bonds between 2 carbons and all hydrogens are assumed.
Okay, thanks.
Professor?
Yes.
If this were a longer chain and we had like an ethyl group, would we still have the alphabetical routine to it?
Yeah, if you have multiple groups, you put them in alphabetical order. If you have, but you don't have to worry about, is the methyl group or ethyl group the lower number? The alcohol will always be the lowest number.
Okay, thank you.
So as we get to more and more functional groups, you lose the ambiguity, because because I'm changing the name, I have to have that as my lowest number, and that's where I began. So it makes it easier to name things that way. Okay. So when you have more than one alcohol, you can use what we used for dienes and trienes, and the fact that we use diol or triol. Okay, so but you still have to locate where they are. So you have to put where the number for each carbon where the alcohol appears. So in the case of having 2 alcohols on ethyl group, this ethyl group here, we're going to have ethane for the 2 carbons. And notice it has the E again, because diol is tacked onto it, that it has to separate the N and the D, so the E is back on there. So we have 1, 2 ethylene diol. Now, if we had 3 carbons in our chain, we'd have propane diol, but we'd have a possibility of having them on 1, 2, or 3. So we have to be very specific and say one of the alcohols on 1, one of the alcohols on 2, and so we have 1,2-propane diol. And then if we go to extend it out and put a 3rd one on there, we would have 1,2,3-propane triol. Okay, so we add the E back in when we do the multiples of di, tri, tetra. It can be as many alcohols as you have. Notice the common names are different. Okay, in the case of common names, glycol means you have 2 hydroxy groups on the same compound. So you have total of 2 carbons, which is ethylene, and then glycol. Okay, it's kind of an engineering term because they make it from ethylene, and so they call it ethylene glycol or dialcohol. And the same goes true for propylene, which is also called propylene glycol. And then the last one we have has a special name for it. It's called glycerol or glycerin. Okay, glycerol or glycerin is a very high boiling liquid that is extracted from the saponification of fats. Animal fats have this triglyceride. And you might have heard the fats in your blood are triglycerides. Well, this is the glycerin portion. This is the triol that has 3 fatty acids hooked onto it. And we'll talk about that in a couple chapters. Okay, now here's where we have to pay attention to prefix, infix, and suffix again, because we have to include that "ene" in there if we have a double bond, or even an "ine" if we have a triple bond. And it sounds weird, but we have to do it. So what we're going to look at for here is we're going to name it with 6 carbons. So we have hex in there as our prefix. We have a double bond, so we have to say hexene right here. But the alcohol is still changing the name. It still goes on the end. So we have all. This should be OL, little o, little l. It looks like a 0, but it's really an OL. So when we have an alkene or alkyne, we have to have your prefix, which is the number of carbons, the ene or ine for the double bond or triple bond, and the all. Now, in this case, because we need to locate where that OH is, we want to put that -1 all in it. So in this case, we have a trans configuration on our double bond here because they're on opposite sides. And the first carbon of that double bond starts on 3. So we have trans -3 hexene 1 all. Okay. Or we could also do E and Z, and it'd be E 3 hexene 1 all. So this is what we call the ene all rule or the ine all rule. That infix, remember, is different. It doesn't name the functional group of the compound. It just tells you about the carbon-carbon bond nature. Okay, so questions on nomenclature. Okay, it's one of our lower priority groups, but it's above amines, and it's below alcohols and ketones and aldehydes. Ketones and aldehydes are the 2 next functional groups above it. So if we only have alcohols and double bonds in there, we're probably going to name it an ene all or an alkane all. Okay, so alcohols are really, really, really important because of that OH group. That OH group has the ability to hydrogen bond. Okay, now we talked about hydrogen bonding being one of the strongest intramolecular forces we have with us, and alcohols are a great example of that. Okay, why do they hydrogen bond? Well, we have more electronegative oxygen next to 2 less electronegative atoms in the case of carbon and hydrogen. That gives rise to a polar bond where we're pulling electron density toward the oxygen, making it partially negative, and leaving the carbon and that hydrogen partially positive. Because it's partially positive, it can sense and start to attach itself to electrons on neighboring atoms, and we call that hydrogen bonding. Okay, so because this hydrogen bonding is one of our strongest intramolecular forces, it changes the properties, including polarity and the boiling point, significantly. Okay, so if we had a molecule that was at the same mass as this methanol here, so if you look at it, we have only about 25, maybe 28 grams per mole molecular weight. That would be it, like ethane, which is a gas at room temperature. Okay, but this is a liquid at room temperature that boils at the 54 degrees, and so everything that's again making it gain that intense change in that boiling point comes from that hydrogen bonding. And if you'll remember that the hydrogen bonding is that attractive force between a partially positive charge on hydrogen, so there has to be a partially positive charge, so it has to have a polar bond, and a partially negative charge on a nearby oxygen, nitrogen, or fluorine atom. Okay, now think about it. Those are the ones with 1, 2, or 3 lone pairs on them. And those 3 lone pairs are available for hydrogen bonding with that partially positive hydrogen. It doesn't pull it away completely. It's just partially charged and likes to balance that charge on the things around it. So what that does for us is it gives a bond strength of about 2 to 5 kcals per mole. And that's enough to significantly change that boiling point. Okay. Now, hydrogen bonds aren't as strong as covalent bonds because the actual OH bond is 110 kcals per mole. So see, it's only partially bonded to there. It's never going to steal it away completely like an acid or a base, but it does allow it to do this significant amount of bonding, and that significant amount of bonding changes the boiling point and melting point, etc. Okay, so what does that really kind of look like? Hydrogen bonding is rarely just one hydrogen to one molecule. So you never just have two molecules participating. So you have multiple attachments because you have multiple partial charges. So in the case here, we're seeing 4 ethanol molecules here. And we're going to look at this one over here. So this one right here has lone pairs, but we don't have any molecules drawn close by that shows that it's hydrogen bond. However, we do have the lone pairs coming off. Let me change colors here. We do have the lone pairs coming off this oxygen here. And so they are hydrogen bonding. The lone pairs are being attracted to the partially positive hydrogen here. And guess what? Another molecule nearby can do the exact same thing. Now, the partially positive side on this molecule can hydrogen bond to a neighboring oxygen. Okay, so that means we can get 3 hydrogen bonds to each and every molecule. Okay, so you have 3 hydrogen bonds at 2 to 5 kcals per mole, but you're doing it 3 times in solution. So you can see why that energy is additive and gives such high rise to our change in properties. Questions on hydrogen bond? All right. Okay, so let's talk about this. This compound is erythromycin A. It's an antibiotic, okay? So what we have is the possibility, not only can it hydrogen bond with molecules nearby, because of its location, it can actually hydrogen bond within itself. And we call this intermolecular hydrogen bonding because it's bonding with itself. It can also intramolecularly bond with other atoms, but it can't do that. Okay, so what we want to look at on this particular thing is, number one, we want to look at the different types of alcohols we have, classifications: primary alcohol, secondary alcohol, and tertiary alcohol. Remember, a primary alcohol is an OH on a primary carbon. Secondary alcohol is an OH on a secondary carbon. And a tertiary alcohol is an OH on a tertiary carbon. So we're going to look for those right now. And then we're going to look at which ones can bond intramolecularly and which ones probably can't based on where they are. So let me blow that up and look at this real quick. So because this is next to an oxygen with lone pairs on it, we can get an intermolecular hydrogen bond. Within the same molecule, it's bonding to itself. And if we look at this carbon here, that's a secondary carbon. So this is a secondary alcohol, okay? So that's just the classification of that. Let's look for another alcohol. We got another one down here, right here. And again, that's on a secondary carbon. Remember, it has 2 other carbons bonded to it, making it a secondary carbon, which turns this into a secondary alcohol, okay? Let's see, that's an ether, that's an ether, that's an ether, that's an ether, okay? Oh, and we have another OH here. And it looks like it has 1, 2, 3 carbons bonded to it. So this is a tertiary alcohol. And it can probably hydrogen bond to this OH, to the lone pair on those OHs. So we can get an intramolecular hydrogen bond. So maybe that's why it looks like that ring is in that position instead of flipped around, because it can do that intramolecular hydrogen bonding. Okay, we have another alcohol here, but it's not close to anything that it can hydrogen bond to, so it's probably not going to hydrogen bond, but it is on a secondary carbon, which makes it that secondary alcohol. And our last OH is this tertiary one here. Again, it's nowhere near anything within the molecule itself, so it's going to probably be not an intermolecular hydrogen bonder, but a molecular hydrogen bonder that is between molecules, not between it. Intra is within itself and inter is between 2 molecules. So, sorry, forgot the word for a second. All right, questions on identifying types of carbon, types of alcohols, primary, secondary, and tertiary. Ethanol was a primary alcohol because it only has one carbon attached to it. These are secondary and tertiary alcohols. Okay. So let's see, I had one other question here. So that gives us the possibility of this being able to hydrogen bond here, this being able to hydrogen bond here. And so it only looks like these three are available for intramolecular hydrogen bonding, where these are going to be intermolecular hydrogen bonding because there's no lone pairs nearby. So, and that's the answer on the slides here. Oh, you can rearrange it. You can flip it around to get a total of 4. So by flipping the ring inside out, we can get a total of 4 hydrogen bonding sites available to us. Notice it had to reorder the ring to get to do it because it was shaped a little differently before. We have to flip this around. We're flipping this around in hydrogen bonding here to be able to do it. Okay. All right. Questions on hydrogen bonding and classifications of alcohols. All right, moving right along. Okay, so let's see the dramatic effect it takes just by having that OH group there in the hydrogen bonding. So I said before that ethane is about 30 molecular weight, and that's about the same molecular weight as our methanol here. Just by molecular weight alone, the methanol should have a boiling point of negative 80 something degrees, okay? But it doesn't. It has a boiling point of 65. And I thought it was 54, but it says 65 here. So that significant change has everything to do with hydrogen bonding. And hydrogen bonding also allows it to be more soluble in water. Okay, it's infinitely soluble in water, so you can mix 100% methanol to 100% water and everything.
Hi, my love. You guys are very needy. Oh shit, what'd you do?
Anna, do you have a question? You're unmuted somehow. Oh, no? Okay. Sounded like we have a dog interrupting us. Okay, so let's look at just gaining a little more molecular weight and see what happens. Just by changing the molecular weight here, we're going from ethanol to propane, ethane to propane. We see that jump in boiling point has everything to do with molecular weight. However, we have about the same molecular weight and we have a much higher boiling point. Has everything to do with the hydrogen bonding. And again, we have a small non-polar portion of the molecule and a polar OH, making it still infinitely soluble in water, while the hydrocarbons are insoluble in water. Okay, let's add another one. So we're gaining a little more molecular weight. That changes the boiling point just by molecular weight by another 40 degrees. And the hydrogen bonding is significantly higher than it was before. And again, it's still completely soluble in water. This OH group can pull in all 3 of these carbons, that nonpolar edge, into the solution. And then it kind of reaches its maximum at where it can pull that hydrocarbon tail in to that polar water. And we drop in solubility by going to the butane, the butanol. And the boiling point goes up, but the solubility starts to go down. So in general, one OH group can typically pull in about 4 carbons. And then to get any more, you have to put in more OH groups. Okay, so one OH group can get 4 carbons into water. And then beyond that, it gets very difficult. So look, by the time we get to pentanol right here, it's barely soluble in water. But by putting an extra OH on here, so this is butane diol, it's completely soluble in water again. But look what the boiling point did. Because we have 2 sites that can hydrogen bond, the boiling point jumped by almost 100 points. Okay. Actually over 100 points right here. Going from 1 alcohol on butane to 2 alcohols on butane jumped over 100 points. And then, of course, that is equivalent to weight to approximately hexane. Questions on the effect of hydrogen bonding on boiling point and solubility. Okay. Now, the next thing we're going to talk about is because that hydrogen can hydrogen bond, it's also acidic. And when we talked about acids and bases, we learned that the pKa of water was around 16 or 15, and the alcohols were just a little bit above that. So alcohols can actually act as acids. Okay, so in most cases, if you have a stronger base, you can act as an acid and and remove that proton to create a salt or what we call an alkoxide. An alkoxide is having an alcohol with the hydrogen removed, and it becomes a really good base. Okay, so if we look at it, just having methanol in water, they both have about the same pKa, which means that it's going to be somewhere in the middle. And so that means that most aqueous solutions of alcohols have the same pH as pure water, which is 7. Okay. However, just like we saw before in those acid bases, there are things that can change the acidity, making them stronger or weaker bases depending on how well they can hydrogen bond. So if we look at our pKa scale, we have something like a strong acid here is HCl, an acetic acid, which can hydrogen bond, but it also has that delocalization, is much more acidic. And then we have methanol, water, and ethanol. Remember, they're completely soluble in each other, and they all have about the same pKa. Propanol is also completely soluble in water and is not, just slightly less acidic. What's happening here is that the more of the non-polar group you're having on there, the less stable that alkoxide is, that deprotonated system is, and therefore it becomes less acidic. Okay, so think of the longer the chains on your alcohol, or the more non-polar the thing is. So this would be their T-butanol, OH here, so it has that non-polar side of it completely. It can't hydrogen bond as well, and because of that, its acidity drops. But they're all in the same range. They're all the 15 to 20 range. Okay. But if we start adding things like electron withdrawing groups to these alcohols, the acidity will go up. Okay. So in the presence of a strong acid, the ethanol can act as a base. Because remember, it has a pKa of 15. A strong acid has a pKa sometimes of negative numbers, or at least highly positive numbers. And so what's going to happen is that it can be protonated. Okay. And so this happens a lot in mechanisms where the first step in a mechanism is to protonate something. And this is very common to use these alcoholic solvents to help transfer that proton from place to place. Okay. So that means that they can also act as bases. So the alcohols can act in bases in the presence of a strong acid. So that means alcohols can be weak acids or weak bases, kind of like water. Water is also a weak acid and a weak base. Okay, questions on acid base? Okay, so one of the really cool things about these alcohol groups is if you deprotonate them, they become very strong bases, right? Because they're weak acids, so they become a strong base, okay? But what's the best way to deprotonate that? Turns out they react with different active metals like lithium, sodium, and potassium. Think about though, you remember the experiments where they throw it in water and it blows up, right? Well, we don't want to do that. But what it's going to happen here is you're actually taking electrons away from the sodium and transferring them to the hydrogens of the alcohol to generate hydrogen gas. Okay, so when you do this, you take one electron from sodium for one of the hydrogens. You take one electron from sodium to another hydrogen, so you can generate hydrogen gas, H2, and 2 equivalents of the deprotonated alcohol, or the alkoxide. In this case, we're using methanol, so we call it sodium methoxide. And it's a really cool reaction. You take an alcohol and you slowly add the metal to it. It'll slowly dissolve and bubble up and give you this very strong base to work with. Okay. So once you have that strong base, it's also a strong nucleophile. So you can use it as a nucleophile, or in the case of things where you have maybe not a great leaving group, you can also use it for a beta elimination reaction. It can pull that hydrogen off on the beta carbon and eliminate something on that alpha carbon to give you a double bond. Okay. Remember, we talked about that when we talked about alkenes, the synthesis of alkenes. So, all right. So then there's another reaction we can do is we can convert the alcohol to an alkyl halide. Okay. Now, this works really well with tertiary alcohols. Okay. So when we think about that tertiary, really reacting well with tertiary alcohols, I'm thinking, you know, we might be going through a carbocation intermediate here because it happens at room temperature and it happens very rapidly. Okay, so what can happen here is you can have a strong acid, it'll protonate your alcohol, that'll give you a carbocation here, and then your chloride can come in and you can get this in very decent yields if it's water soluble. Okay. However, primary and secondary alcohols don't do this. Okay, so that should alert you to say, hey, primary and secondaries don't do it, but tertiaries do. Probably goes through a carbocation intermediate. Okay, now, however, if you have water insoluble alcohols, you still can do this under dry conditions. So you have to eliminate the water. Notice we have 7 carbons here, so that won't be pulled into water by hydrogen bonding because it's more than 4 carbons. And we can do it under dry conditions, so it does eliminate a little bit of water, but we're in a solvent right here. So again, it's undergoing the same thing. It's going to protonate our alcohol. It's going to eliminate, giving us our carbocation and give rise to our our halogenated substrate. Okay. Now, this does work in primary and secondary alcohols if we have HBr and HI. Now, if you'll remember our nucleophilicity chart, Br and I are good nucleophiles. Chlorine and fluorine are fair nucleophiles. That's why we can do it with HBr and HI, but we cannot do it with HCl under these conditions. Bromine and iodine are strong enough nucleophiles to make this reaction happen, even without forming that carbocation. It does take a little more heat, though. Okay. Now, so here's the mechanism here. First step is a very familiar one. We have an acid, we're going to protonate. Okay. Once we protonate that, we create this oxonium ion. And the reason that's such a good thing is because when you eliminate this, it eliminates as neutral water. So that makes it a better leaving group instead of hydroxide ion, which is a very strong base, which is a very bad leaving group. So we protonate our alcohol first. And then that gives rise to our breaking a bond to form a stable molecule. In this case, the tertiary carbocation. Okay, that tertiary carbocation can wait around, it can react with water, and it can reform again. So it can do anything it wants. However, in the presence of a fair nucleophile, in this case chlorine, it can then reattach to form that new carbon-chlorine bond and give us our product. So our tertiary alcohol with HX in the presence of water is because of that protonation and that liberation of water at the end. Okay. However, it's a little bit different in the primary and secondaries because we don't form a carbocation in primary and secondaries. We still do the first step. We add a proton to make the OH a better leaving group. And in this case, we form again the oxonium ion here. And now it's just ready to leave. It can leave and be a neutral species. So it has to wait for a good nucleophile to react with it to kick it out. And so the next step is, of course, having a good nucleophile. The bromine or iodine can come in and do a backside attack, kicking out neutral water and giving us 2 neutral species out the end of the reaction. Okay. So we end up with similar products, but we have different mechanisms based on the type of compound we have. So this is an SN1 reaction because we're forming a carbocation, and this is an SN2 reaction because we waited for the nucleophile to kick out our leaving group. Okay, so just like the other reactions in nucleophiles we talked about, if we have a secondary alcohol, it gets increasingly more SN2-like. You can occasionally form a secondary carbocation, but it's not as favored. Tertiary will always react with that SN1 character. Primaries will always react with the SN2 character. Secondaries can do a little bit of both, and you can actually see that by your product mixture. You can force it one way or another by having the better nucleophile is going to make it go SN2. The poorer nucleophile is going to make it go SN1. Okay. And it's a combination of sterics and electronic effects. So if we want a really good, reliable way to make a primary alcohol converted to a primary alkyl halide, we actually have a special reagent for that that makes it a better leaving group. Okay. Because the chloride ion is not strong enough to just displace OH in the presence of an acid as a primary, we use a reagent called thionyl chloride, SOCl2. Okay, let me draw that as OSClCl. Okay, so, and the way this works is it actually reacts with the alcohol to form an oxygen-sulfur bond to create a better leaving group. So let's see, we don't have that. Okay, so the mechanism, I'm not going to go into right now, but what happens is we end up having this S bind to the oxygen to make it a better leaving group. Then one of these chlorides can then kick out that group. So notice the oxygen is transferred to the sulfur here. We end up with SO2. We generate a little HCl, and the other chlorine goes here. So the hydrogen goes to the HCl, the oxygen goes to the SO2, and the last chlorine goes to the new bond with carbon, giving us our alkyl chloride. Okay, so know this reaction? I think it's on your homework. Okay, and it's the best because we can't do it with just HCl. We must use this reagent. Okay, so the other thing we can do with alcohols is we can do what we did by creating a beta elimination. This should be a beta right here, beta elimination. So you have an alcohol, and you're going to take the OH off one carbon and take a hydrogen off an adjacent carbon to give you an alkene. We did this under alkenes. We saw that primary alcohols were really hard to do. We had to heat them very high but it doesn't have the ability to go through a carbocation intermediate. And so it has to be a beta elimination. Your base has to come in and pull on your hydrogen while your alcohol is protonated. Secondary alcohols will do it at a little bit lower temperature because it has a little more of that carbocation character, and it can do that. Tertiary alcohols often can be done just above room temperature. Because you have that opportunity to form that carbocation, you can protonate your alcohol, have it leave, give you a carbocation, and then the hydrogen can be pulled off by even weak bases because those electrons kick in and form your double bond. Go review the chapter 6 about dehydration of alcohols to form alkenes. Okay. So in the case of our primary alcohol here, we have to protonate our OH, and then we have to have something in there act as a base, which happens to be the deprotonated acid can pull the hydrogen off of the other side. The hydrogen came off this side here to give us our alkene and water. Okay, but because it's not a very strong base, it takes a lot of heat. Okay, moving up to a secondary alcohol, it doesn't take as much heat, but it gives us the same thing. Removes the OH from one carbon, removes a hydrogen from the other carbon to generate water and to generate our alkene. Okay. However, once we go to our tertiary, we can actually protonate this and eliminate the water ahead of time, and then it just takes anything can come along, and any old base, any weak base can come along and remove that hydrogen, leaving those electrons to form that new pi bond. And notice this is just above room temperature, which is 20 to 25 degrees C. Questions on dehydration? I'm hoping this sounds like review to you, but it is a reaction that alcohols happen to do a lot. Okay, now when we do this, when we eliminate an OH group, we're going to do what we call Zaitsev's rule, which you will always have the greater number of substituents as your dominant product, as your primary product, okay? So think about the stability of alkenes. Monosubstituted alkene is less stable than a disubstituted alkene, which is less stable than a trisubstituted alkene. That's why we follow Zaitsev's rule. You always want the more substituted one whenever possible. Okay, and so when you're thinking about this, you'll know if I remove my proton from this side, I'm going to get to my monosubstituted. But if I remove my proton from this side, I'm going to get to my disubstituted. And so that's going to be our major product. Questions on that? Okay, moving right on. All right. So let's do our dehydration of a secondary alcohol. It's going to give us our three-step mechanism because we're going to have the first thing is the addition of proton because we're having an acid catalyzed dehydration. So the first thing we're going to do is protonate our alcohol, giving us, again, the oxonium ion right here, the oxonium cation, which makes it a better leaving group, right? So now we can then go ahead and go through a slow step, which is creating that secondary carbocation. Remember, the secondary carbocation is not as stable, so that's why it's the slow step. It's going to take a while for it to form. But as soon as it does, water can now act as a base because water now has these two pairs of electrons that it can reach out and make a new hydrogen bond for. It's going to act as a base and pull off this hydrogen here because it's just ready to go. It's ready to swing those electrons in to create our new pi bond and regenerate our acid, our hydronium ion. So notice this is catalyzed because we protonated our alcohol first, we waited for it to dissociate to give us our secondary carbocation, and then we used our water as a base to regenerate our acid. Okay, so we would call this an E1 reaction because it goes through the carbocation intermediate. Okay, in the case of primaries, we can't do that. Obviously, the tertiaries would always go through that tertiary carbocation. Primaries, we can never form that primary carbocation. So we do the same thing. We add an acid catalyst to generate our oxonium cation right here. But now we have to use the remaining water as our base. So we have to have a bimolecular E2 reaction where the water comes in and starts to act as the base first because we can't generate that carbocation. So then that allows these electrons to kick in to form our pi bond and allows this sigma bond to break, giving us neutral water. So it's bimolecular because we have to pull on this hydrogen first with our base to allow the electrons to transfer in and out to give us our leaving group and our new double bond. Okay, because we cannot form that primary carbocation, so we must do that bimolecular reaction. Okay. Okay. So, well, if we can dehydrate something by removing water, we can make alcohols by hydrating. doing the reverse reaction. So how would we do that? Well, it's just the reverse reaction. We take that OH and we add it across that double bond. Okay, so that means that this acid catalyzed dehydration and the acid catalyzed hydration are in equilibrium. Okay, so how do we force it to go one way or the other? Well, that's easy. You want it to, if you want it to go to where you have more of the water reacted, you add a lot of water. More water, it's not going to want to eliminate water. It's going to want to add the water across the double bond. And so if you want to have the alcohol, you add a lot of water to your system with your acid, and it will give you the alcohol. If you want the alkene, you find a way to remove the water from the reaction. If you're removing the water from the reaction, it's going to generate a little water, but then by removing it, it can't do the reverse reaction, and you're going to drive it continuously to the alkene. So even though this experiment is in equilibrium, you can force it one way or the other by controlling the experiment. Add water for the alcohol, remove water for the alkene. Okay. All right, questions on that. So we did a lot with alkenes. We looked at our alpha and our beta eliminations. So we had our E1 and E2 reactions with water being lost. We now know we can make an alcohol from an alkene by doing the reverse of an E1, E2 reaction by adding excess water. What else can we do to alcohols? Well, let's see. Well, we could probably oxidize alcohols to turn it into a new functional group. Okay. So what do I mean by oxidize? Okay. So oxidizing is the removal of hydrogens or the addition of electrons or the addition of oxygen. Okay. So if you think about it, if you're adding oxygens to a system, it's being oxidized. To add an oxygen to a system, you have to remove hydrogens. So removing hydrogens is also a form of oxidation. Okay. So we can oxidize primary alcohols to give you an aldehyde or a carboxylic acid, depending on which conditions you choose. Okay. So primary alcohols have hydrogens on the carbon that the OH is on. So it can be taken to an aldehyde or a carboxylic acid. A secondary alcohol only has one hydrogen to remove on the carbon, one hydrogen to remove on the oxygen, and that will only give us a ketone, that C double bond O. Tertiary alcohols don't have a hydrogen adjacent to the alcohol and therefore do not oxidize. Okay. So primary can give one of two products, secondaries give one product, tertiaries don't react. So let's talk about our most common oxidizing agent. The most common oxidizing agent we have is what we call chromic acid. Okay, by taking chromium oxide, water, and a little bit of acid catalyst, you can generate this very oxidizing system. And what's happening is the chrome is going to go from chrome 6 to chrome 7. And in that process, it's oxidizing your material. So what does that look like? Okay, so in the case of this, if we do it in water, we're going to have an alcohol that is going to, we have two hydrogens here. I'm going to draw the hydrogens out separately. Okay, so the first step is we're going to remove a hydrogen from our OH and a hydrogen from our carbon, and that generates a double bond, right? We're removing those hydrogens just like we did with that dissolving metal reaction with the sodium. We're removing the hydrogens, taking them somewhere else. But in this case, we're actually going to generate a double bond. And so the first thing we create is this aldehyde. Okay, so we know it's an aldehyde because it has a carbonyl bonded to a hydrogen, so that gives it an aldehyde. However, this right here will react with the water in the system, and therefore it can be oxidized again. And when it's oxidized again, we put another oxygen on there, and this gives us an OH group. And so we have a carbonyl with an OH, giving us a carboxylic acid. Okay, so we're going from octanol to octanal, which is the aldehyde, to octanoic acid. Okay, Now, we can't isolate this because this is just as reactive toward the oxidating conditions as the alcohol is. Therefore, it always goes directly to the carboxylic acid. Okay. Again, if it was an aldehyde, you'd have one hydrogen on that carbon to remove. It forms the carbonyl, and it's done. Okay. So how do you stop it at the aldehyde? Well, we have a special reagent for this, and we call it PCC. PCC will stop at take a primary alcohol to the aldehyde and stop there. It will not continue on. So let's talk about PCC. PCC is we're still using chromium oxide in our system. We're adding a little bit of acid to it right here, and then we're adding pyridine. Okay, pyridine is one of those bases we talked about. Okay, so what's happening here is we're making our pyridine salt here, which counterbalances this chromium salt here, and it makes it soluble in things other than water. The chromic oxide would only dissolve in water. It would not dissolve in any organic solvent. By making it this pyridine salt, it now allows it to be pulled into organic solvents. And in the absence of water, you can stop at that aldehyde. In this conditions right here, you had water here. The water reacts with the aldehyde to make it reactive and makes it easy to oxidize. In the case of the PCC, we make it an organic solvent, soluble material, and we can stop at the aldehyde. So in most of the time, what we see in the conditions are, we have a primary alcohol, we have PCC, and then we have this as our solvent right here. This is just our solvent. It's called methylene chloride or dichloromethane. Okay, it's a really common solvent. It doesn't contain water. And because it doesn't contain water, the oxidation stops at the aldehyde. So write down PCC stops at aldehyde from a primary alcohol. Okay, so it'll go there. Without PCC, it goes to the carboxylic acid. All right. Questions on oxidations, reductions, eliminations of alcohols? Okay, I think we have about 20 more minutes, so I'm going to continue on. And we're going to talk about a new functional group here, the ether. Okay, the alcohol was specified by a carbon-oxygen-hydrogen bond. And that gave us something that did hydrogen bond and gave rise to its properties. Okay. Now, if we take that same system and replace that hydrogen with a carbon, we have a new functional group called an ether. It's distinctly from the carbon-oxygen-carbon bond, and which means the ether itself does not hydrogen bond. But things with hydrogen bondable hydrogen can bond to ether. Okay. So the oxygen's sp3 hybridized and therefore ideally would be 109 degrees. However, the methyl groups are a little bit bulkier than the lone pairs, and therefore the angle is a little bit bigger, around 110.3. So, and notice that when we have that valid Lewis dot structure here, we have both lone pairs represented. Okay, so ethers never change the name. They are always a substituent, okay? So in Iupac, what we're gonna do is we're gonna take the longest possible chain we have, and then the other smaller chain, we're gonna call it the alkoxy group, meaning we'll have whatever the art group is. Let's say it's a propyl group, your main chain's a butyl. So you're gonna have propyl oxy butane, because the longest chain first, and then the oxygen with the shorter chain is a substituent. Okay, so let's apply that with Iupac names, and I'm also going to tell you a couple common names. Okay, so here we have our main chain here is the two carbons. Notice it'd be the same on the other side, but we have to pick one as the main chain. And since they're both the same size, we're going to pick one arbitrarily. And then the other part of the molecule becomes the substituent. Okay, so in that case, we have ethyl right here, and we have ethane. Okay, but we have an ethyl group, but we have the oxy. So it's going to be F-oxy. Oh, let me actually change the color I'm circling it in. The F-oxy is the substituent, and the ethane is the main chain. Okay, a little hard to see in this one, so let's move over to the next one. In this next one here, our main chain is 1, 2, 3 carbons. Okay, and that's wrong. It's 3 carbons, and we have a methyl group as a substituent, and we have a methoxy. We have a methyl group with an oxygen as the other substituent. 3 carbons was our longest chain, so that should give rise to the name propyl. Prop. And so that'd be propanol. No, that's not right. Should be propyl. No, that name's completely wrong. Oh my gosh. Okay, let's do this. Start it from the beginning. We have propane right here. So propane right here. We have a methyl substituent and a methyl with an oxygen on it. So we're going to have 2 methyl, 2 methoxy, and then instead of this, we're going to write propane. Okay. So in this case here, it also has a common name. It's a common additive used in gasoline, and it's called T-butyl methyl ether. Okay. When we name common names in ether, what we do is we name one substituent, the other substituent, and we put the name ether after it. So in the case of this one here, we had an ethyl group, and we have an oxygen, so we call it diethyl ether. So the Iupac name is we find our longest chain, and then the rest of it's a substituent as the alkoxy substituent. In common names, we name one side of it, the other side of it, and then add the oxygen by saying the word ether. Okay, so let's do something a little harder right here. So we have our main group here is going to be the cyclohexanol. That's the longest chain, and that's how we're going to name it. So we're going to name cyclohexanol, which means this ethyl group here is our substituent. So our name is going to be 2-ethoxy cyclohexanol. Now this happens to also be in the trans configuration, so we actually have stereochemistry we can play with. And if we quickly assign our hydrogen back here, we have 1, 2, 3, which is clockwise, giving us R. And we have our O8, our hydrogen sticking out here, which still gives our priority of 1, 2, 3, which is counterclockwise, but it's reverse. So flip it over and we have R. Bet you didn't think you were going to use R and S after the test, but that's not true. Okay, so a Iupac name is longest plus alkoxy, common names, both alkyl groups, and then add the word ether.
I have a question.
Sorry.
Oh, sorry.
Go ahead.
Sarah,
I was just going to ask.
Okay.
So the hydroxyl group is carbon 1?
The hydroxyl group in alcohols. Oh,
In the last example. In the hexanol.
Alcohol, in rings, whatever changes your name is always position 1.
So the ethyl, or I guess the ether wouldn't change the name?
No, ether is always a substituent.
It's okay. Okay.
Ether ranks below alcohol. It doesn't even change the name. It's like halogen. It's like fluoropropane. It's just a substituent. It's always a substituent.
Okay, thank you.
For that cyclohexanol, are you able to name it trans?
You could name it trans because they're on opposite sides of the ring, yes.
Okay.
But the RNS is slightly more precise, but trans would identify it as that specific isomer, yes.
Okay, thank you.
So we actually use cyclic ethers quite a bit. And we have to name them slightly differently because you don't have a group, a main chain, and a substituent. So you actually they name it for the actual structure it makes. And so they have special names. When you have 2 carbons and an oxygen and a 3-ring thing, this is called oxapropane, as its real name, but its common name is called ethylene oxide. And if you think about that, it was an ethylene, and then you added an oxygen to it, so it's ethylene oxide. Okay. If we expand that ring out to be a 5-membered ring with an oxygen in it, we call that tetrahydrofuran. And that's because it's based on a molecule that has 4 of its hydrogens removed to make it into a ring with an aromatic ring. We'll talk about that in the next chapter. And so they add 4 hydrogens to it, and it's called tetrahydrofuran. This is a very common solvent. It has a very funky smell. And then there's this one right here. This is an isomer called 1,4-dioxane. This is not the same thing as the dioxin-based pesticides you heard about, although this subgroup does exist in the compound and is where it gets its name. This particular compound is not as toxic as the diphenyl dioxanes, which are the ones that used to be used as pesticides and are still environmentally found 30 years after they stopped making them. Okay, so physical properties. Ethers do have dipole-dipole moments, okay? But because it's a covalent bond, there can only be that weak dipole-dipole interaction between molecules. And if something else has a hydrogen bond, it can hydrogen bond to it. So because the ethers don't hydrogen bond, they only have those dipole-dipole moments. They usually boil lower in temperature than if you had an alcohol of that same molecular weight. Okay. Hydrogen bonding is our strongest force. Dipole-dipoles are next force. Okay. So let's look at that as function of not only boiling points, but solubility in water. So remember, the alcohols were soluble in water because their ability to do that hydrogen bonding. Okay. Ethers don't have that. Ethers do have dipole-dipole, so there's going to be some solubility and some change in molecular weight. Okay, so if we look at this right here, this is ethanol and dimethyl ether. Okay, they have the same exact molecular weight. In fact, they're structural isomers. Okay, they're changed functional groups by changing connections, and one is an alcohol and one is the ether. Okay. Even though they have the exact same molecular weight, the ether boils almost 100 degrees lower because that lack of hydrogen bonding. And it's very poorly soluble in water. Okay. The alcohol is completely soluble in water. Okay. Let's go up a couple more carbons. Remember that butanol, that OH was barely pulling those 4 carbons into that water? Well, we have that same thing. It's barely pulling that in there. But we have that dipole-dipole interaction allowing about the same amount to be pulled into water as well. Okay, so we have less solubility in water than the alcohols because of lack of hydrogen bonding, but we still do have dipole-dipole forces. Okay, by the time we get to pentanol, it barely goes into water. Adding that extra alcohol to it makes it completely soluble in water. And then by changing it to have 1 ether, we have a slight solubility in water, but this is supposed to have 2 ethers. There's supposed to be another ether right here, an OH there. So we have 2 methoxys on an ethyl bridge. That's completely soluble in water. So having those 2 hydrogen bondable oxygens available to it makes it soluble in water. Let's look at boiling points though. In the case of the pentanol, we only have 1 thing that hydrogen bonds and we have a high boiling point. In the butane diol, we have 2 things that hydrogen bond and we have the highest boiling point. By taking away the hydrogen bonding, our boiling points are both below 100 degrees. Okay. So the driving force here is that you only have dipole-dipole forces. You lost the hydrogen bonding you had with the alcohols, and that affects both its solubility in water and its boiling point, even with similar molecular weights. All right, so, but that doesn't mean the ethers don't hydrogen bond. They can be hydrogen bond acceptors only, okay? Which means that we can have water hydrogen bond to it, but the ether itself doesn't have a hydrogen to bond. So the water is hydrogen bonding with the ether is not hydrogen bonding with the water, okay? So that's why the ethers can be slightly soluble in water because of this interaction. Now note, there's only one available. Actually, you could probably get two, you might be able to get two hydrogens bonding, one to each of the lone pairs on that oxygen. But usually because of sterics, you can only get one molecule of water in there to bond. Okay? And as these groups get bigger, we get less and less of that interaction. Okay. All right, so because of this, we see a significant difference in the boiling point, melting point, because of that lack of hydrogen bonding. Even though these are structural isomers and have exactly the same molecular weight, we have hydrogen bonding here. We have only the dipole-dipole interaction here. Okay, so ethers don't really have a lot of reactions, okay? They tend to have a very strong carbon-oxygen-carbon bond. And so they tend to not really react very much with strong oxidizing agents like chromic acid. And they don't react with most acids or bases at moderate temperatures. Because of the strong carbon-oxygen bond and there's no hydrogen to easily oxidize off, they are relatively stable and are used as solvents for a wide range of reactions because they are so stable. The other thing is they don't have the hydrogen bond, that hydrogen-hydrogen bond, so they are not acidic either. So it's a non-acidic solvent that isn't easily oxidized or reacted with. Okay. That's for all of the ethers except for one. One ether is very, very reactive, okay? And that's that cyclohexapropane that you're talking about, or the epoxy group. Notice this is the ethylene oxide right here. And it's created by taking ethylene, oxygen, and a little bit of silver catalyst, and it turns it into ethylene oxide, which is what the name is right here. So the key here is we have a three-membered ring, okay, with an oxygen on one side. What this means is we have ring strain, okay? We have an ether that's normally chemically non-reactive, but we have this really tight ring. These are all sp3 hybridized atoms. They want to be at 109.5 degrees. We're forcing them to be at 60 degrees. That's where the reactivity of the epoxide comes in. It's the one cyclic ether that has a lot of reactivity, okay? And so we have a way for it to open up whenever you attack it with a nucleophile. Okay. So if we have the general epoxide is just with any groups on here, those could be hydrogens, those could be R groups, doesn't matter. If we only have hydrogens on there, we call it ethylene oxide. And ethylene oxide is also used as a sterilizing agent for medical equipment. And if we have our, add an extra group here, so we have a total of 3 carbons in our chain, we have propylene oxide. So, well, how do we make this? If that ring strain is so hard to make, how do we make this? Well, we have to trick it, okay? And we trick it by adding a really, really weird oxidizer, a thing we're calling a peroxycarboxylic acid. What that peroxy means, it means it has an extra oxygen on it, okay? So if you think about acetic acid, it's just one OH and a methyl group here, right? We're adding an extra oxygen, okay? When we add that extra oxygen, we now have an oxygen-oxygen bond here. That's a very weak bond, and so it doesn't want to be there. So what it wants to do is it wants to rearrange itself, get rid of that oxygen, and go back to being its stable carboxylic acid. Okay, so our peroxy acids or peroxyacetic acid are going to be able to oxidize that alkene, giving away that oxygen, generating our epoxy. Okay. So that generally all we have to do is have any alkene present. And I'm going to draw this one right here. And we have a peroxy acid, and that's going to generate our ether. And notice, because of the fact that we have a 3-membered ring, that obviously both of the bonds to that are going to be on the same side of the ring. Okay, so we're going to, since we just made this with our per acid from our cyclopentene, let's see what kind of things we can do with it now. So now that we have this, it's reactive because of the ring strength. Normally, ethers are just nice and stable. You can boil them in water, boil them in acid, boil them in. As long as there's no ring strain, it's fine. It just handles it. It doesn't do anything. However, because we're so strong, because we want to be 109 and we're at 60, it's likely to get ring open by adding anything that's going to come in as a nucleophile and generate a new sigma bond. It'll spring open and give us our reaction. In this case, in the presence of water, it'll ring open and give us, instead of being an ether, it's going to give us a diol. And the cool thing about this is the stereochemistry. Because the epoxy is on one side of the ring, the oxygen has to come into the bottom side of the ring. And so you always end up with the trans diol from this reaction. So epoxies will open up, and if they're in a ring or in a system where they can't free rotate, you're going to end up with a trans diol. Okay, so how does this work? I'm going to go through the mechanism. That's the last thing we're going to do today. And then we'll come back on Thursday and finish up this chapter and talk about aromatic rings and benzene. Okay. So here we have the first step in our system is that it's an acid catalyzed hydrolysis. So we're going to add a proton. So we're adding a proton to the oxygen on the epoxy. And what does that do? That makes it a better leaving group because it can leave as a neutral group. Okay. So because now it's a better leaving group, we can have a weak nucleophile. In this case, water. Water is a weak nucleophile. We're going to take one of those lone pairs over here, come around from the other side, because this side's being blocked by the oxonium ion here. So we're going to come around to the other side and knock that open, and springs open the oxygen on this side, having the OH on the bottom side. That's why we get that trans configuration in the diol. And when it opens up, we still have our protonated species, which can be deprotonated by water to give us our neutral final product. And again, notice the trans configuration here. The nucleophile had to come in from the backside, or the bottom in this case, and the OH was already, the O from the epoxy was on the top, giving rise to that trans configuration. All right. Questions about epoxies, okay? It's one of the only things ethers do. It only is a 3-membered ring, and it's driven by the idea that it just wants to open up that ring. Okay, so why is that important? One slide. Is that you can attack it with any nucleophile to achieve a whole bunch of different functional groups, okay? So because it wants to ring open right here, we can hit it with ammonia. Ammonia is a nucleophile. It has a lone pair. It's going to come in from the other side and generate. Notice it's going to come in and give you to the least substituted side. It's going to come into the least substituted side and give you an amino alcohol right here. And the alcohol is going to be on the more substituted carbon. In the case of water here, we really can't tell which oxygen is which, but the OH is going to come in, add on to the other side, giving us a glycol or a diol. Remember, two alcohols on the same thing as a diol. Or we can attack it with a really good nucleophile here and create a Thio alcohol, okay? Now, because the thiol is lower priority than the alcohol, we call it a mercapto alcohol. Here. And so these give rise to a bunch of different places that we can use in pharmaceuticals and pesticides and food additives, where we can just open up this ring and have a nice, consistent molecule by attacking it with a variety of different nucleophiles. All right, we're here at 12:20, right on the nose. So I'm going to go ahead and stop recording. If you have questions, please stay behind and I will answer them. If not, head on and I'll post this as soon as it processes.